Have you ever built an antenna switch, an SWR bridge, power sampler, or many other things which ended up having an unacceptable SWR? Or maybe you didn't check. An SWR bridge can measure power SWR accurately and still may present a poor SWR to downstream devices. Seemingly good RF wiring may not be all that good at all. So can we use SimSmith to help explain what's going on? Here's a little calculator at EE-Web that kind of describes, we can make it kind of describe wiring for us. In a 50 ohm system, it's pretty hard to build a 50 ohm, it's pretty hard to do 50 ohm wiring. Let's assume for a moment that we've got number 12 wire, which is about 80 mils in diameter, and we've got a case that's an inch away from the wiring with a dielectric of 1, which would be air. That represents approximately a 237 ohm transmission line. Maybe we've got, I don't know, maybe we've got a case on both sides of the circuit. Again, we'll make the wire diameter 80 mils. The substrate height now will be, let's say it's an inch on each side. So it's a 2-inch high box. Again, the dielectric is 1. 12 gauge wire, that's 166 ohms. If we put a flat piece of wire in there instead of round wire, make the wire say 5 mils thick, make the wire maybe 300 mils wide, put it, let's say, a half an inch above the case, again with a dielectric of 1, 154 ohms. As should be becoming pretty obvious, it's pretty hard to build a 50 ohm structure. We can build one if we really want to, but it becomes very difficult. So if we start off with number 12 wire again, dielectric of 1, and let's just reduce the height here down to like 10 mils. At 10 mils, we've got 41 ohms. Impedance, 15 mils, 50 ohm. So if the 12 gauge wire was 15 thousandths of an inch above the case, you'd have a 50 ohm structure. That's pretty hard to achieve, and you can achieve that. I mean, you can for short runs you can put insulation underneath of it, which will have a dielectric maybe of 2 if you put like a piece of Teflon under it, and that will drop the impedance down even more. Maybe we put it 20 mils above the case, and be close. But for most wiring, you'll find that you end up with a much higher impedance than 50 ohms, which is unfortunate. So let's bring up SimSmith and see what that means to us. So if you believe what I just basically said, that we've got a piece of transmission line, and let's make this piece of transmission line, it's going to be air, it's going to have an air dielectric, so let's set its velocity factor maybe about 0.93. Give it low loss because there's no dielectric in there, and we're going to use big wire, and let's make it say a half of 0.5 feet long. That's like an antenna switch. It might take a couple inches to get in, an inch and a half to get into the switch, an inch and a half out, and a couple inches in the switch. And its impedance, let's say it's 190 ohms. The reason I'm using this number is I measured some stuff that I built years ago, which I've kept around, I don't know, mainly for posterity reasons. I just kept it around. I measured some of it with a network analyzer, and I got curves that looked very much like this. If I put a 50 ohm load on the output, good 50 ohm load, calibrated a VNA into the device under test, I would see an impedance that would look like this with frequency. These two circles represent the top of 10 meters basically, and the top of 6 meters. At the very end up here at the X represents pretty much the end of, let's make it even go further. It represents the end of, say, 2 meters up here. So this represents a pretty bad SWR. At the top of 10 meters, we have an SWR of roughly, zoom in here to get the, okay, let me use the right number of points here. 29 megahertz, we have an SWR of 1.4 to 1, a little bit more than 1.4 to 1 on 10 meters. On 6 meters, we'd have 1.9 to 1 SWR. And you might not be very happy with those results. What can we do about that? Well, we can certainly try to reduce this number, but you'll find that reducing this down much below 150 ohms gets to be very difficult, and you end up having to have very wide traces, or very wide like strips of copper and stuff rather than wire. And it becomes just kind of, a little too difficult to do. So what can we do about this? We know in the structure that we have, what we have is coax generally, or transmission line in general, has a characteristic impedance or surge impedance that's pretty much the square root of L over C per unit length. So we have L matching the same thing as we have in the coaxial structure a lot of times, but the C is too low. And since it's L over C, that means the impedance rises. So we need extra capacitance in this circuit to basically make this match better. Let's see what happens if we were to put a little capacitance in that circuit and see what happens. Let's start with a small value. And we can see as we increase this value, indeed we are getting to be a little bit better of a match. Certainly we're not able to get the match to be really good, but we're able to make it better. What happens if we were to put a capacitor on both sides? We're doing better yet. So eventually we can come up with some kind of a, that's not too bad. For 10 meters and 6 meters and everything below that, that's a very good SWR. It still is pretty bad on 2 meters. If we go to 2 meters down here, we're basically, SWR is 5.5 to 1 on 2 meters, which is not good at all. But this is a reasonable way to match that. Many commercial products will have things inside them that look like, I don't know, they almost look like they're accidents, but they end up being capacitances that they've put in to try to match stuff a little bit better. This is one way possibly to do it. It's easy to match at the end points. It's a little more difficult to match in the center, but we can certainly match in the center. We can delete these capacitors. We can change this piece of transmission line to be 2 pieces of transmission line in series. We can put a capacitor in the middle and see what that does for us. Well, if we only want 6 meters and 10 meters, that's pretty good. Putting it in the center, single capacitor. So is this going to be good enough for us, or what do we want to do? I want to build this antenna switch, and I want to make it work on 2 meters. And I want to see if I can get SimSmith to help me actually make it work on 2 meters. So let's think about what that means. If the center worked and the outside didn't work before, what's really wrong? Well, on 2 meters, we have too much of a wavelength in here before we do compensation. If we really wanted to compensate these pieces of coax very well, we put lots of little capacitors every few tenths of an inch. We'd put a few fractional picofarad, and it would be an incredibly good transmission line that would be 50 ohms. We don't want to do that everywhere. So let's see what happens if we try to put 3 capacitors in. Let's see if we can possibly get a better match. 3 capacitors were separated by 1/4 of a foot, so 4 inches. 4 inches is a significant wavelength, a piece of wavelength on 2 meters. 2 meters, a quarter wavelength is about 19 inches, so 4 inches is about 1/5 of a quarter wavelength, a 20th of a wavelength. Let's see what that does for us. We obviously have way too much capacitance right now because each of these capacitors were the same value as the single one was before. This is a really powerful feature in SimSmith, the ability just to drag this stuff around and see what you get. Real time, not have to hit any kind of funky run button or anything else to get a measurement. I mean, I've done here now probably 100 measurements. Pay attention here. Maybe I can get this to work a little bit better. I'm becoming a little bit anal about this, it looks like. All right, this circle right here is a 1.1 to 1 circle, and everything from 150 megahertz down to DC is well within a 1.1 to 1 circle by compensating the 3 points. If we make this circle be 1.05 to 1, we're still within 1.05 to 1. We could certainly get there if we really want to. Heck, that's probably within 1.02 to 1. Anyways, that's an extremely good match. I mean, if you look at the Smith chart when it's zoomed out, you see hardly anything. So, is there any reason to actually do this in an antenna switch? Well, in an antenna switch, the SWR that you get, you really don't know what the load impedance was. So let's pretend for a moment that we had a system where we already had a 1.5 to 1 SWR due to our antenna. I'm just going to make this be 75 ohms to give us a 1.5 to 1 SWR. I should have made this 50. Let me go back to 50 for just a second. I'm going to put something in here that gives me a 1.5 to 1 SWR. I'll use an inductor for this part here. And there's a 1.5 to 1 SWR. And let's make this 1.5 to 1 SWR occur at 10 meters. So 112 nanohenries here gives me a 1.5 to 1 SWR at 29 megahertz. Let's set this to be just 29 megahertz. And there we are. Now, if I put a 75 ohm load here, that's another 1.5 to 1 SWR, and our SWR is higher. Well, can we predict how much higher or lower it is? And we certainly can. We can put a piece of transmission line in here. Let's put a fairly lossless piece of transmission line in here. We don't really care what the velocity factor is. And let's just basically sweep it and see what happens. If we want to sweep it, we need to sweep it up through a half of a wavelength. So let's make 180 degrees. That's 11.3 feet. So if we come down here and we set the piece of transmission line going from 0 to 11.31 feet, 100 steps is fine. And we're going to sweep it. This is a small bug that exists in SimSmith. I've swept from 0 to 11.31, and it seems to think that you can't sweep across the sign. I have to go here to make this be point. This should fix it. Okay, that's effectively 0. If I sweep from 0 to 11.31 feet, I get this locus of SWRs. There is a distance here. If we look at it on this chart, it might become more easy to see. There is a point right here at 2.514 feet of transmission line where this 1.5 to 1 SWR is exactly canceled out by this 1.5 to 1 SWR. There's also a place where the two 1.5 to 1 SWRs actually combine to become 2.246. The SWRs almost become, it seems like they just about become the square of the two SWRs. I don't have a proof for that, but that happens pretty regularly. And we can demonstrate that differently. We can make this, instead of 75 ohms for our 1.5 to 1 SWR, we could take 50 and divide it by 75, or divide it by 1.5. And that's 33.333 ohms. We could put that in there. And of course, we still find a place where it matches, and we still find a place where the SWR is 2.24. So the reason to do the matching I've described is because if we have other SWR in the system, it just continuously can continuously degrade the system. If we had 2 or 3 devices that all did the same thing, you might be lucky enough at one frequency to have them all match, but more likely they won't all match, and it's impossible to make them all match in a broadband case. In a narrowband case, a solution like this right here looks pretty good. But if I leave the cursor right there and I go back here like I did before, and I say the impedance was 75 instead, now look where I went. At this point right here, I'm up here near the maximum. So, fundamentally, it's good to have each individual device on its own merit have good SWR. And compensating is this thing that SimSmith shows us how to do that very, very well. One thing I didn't mention before, did I lose the other one or not? I think I did. We can do a simple match here again, and I'll demonstrate this one more time. If we start off again with our piece of transmission line, which is going to be a 1/2 foot long, 190 ohms, 0.93 velocity factor, 0.25 feet long, 2 of those, just like we did before. Rematch that again. This was about 22 if I remember correctly. This was like about 8. This was like about 8 also. Sweep from 1 to 150 megahertz. And we got to start with 50 ohms. There we go. All right. Now, SimSmith does exactly what you tell it to do, and if you don't pay attention to what you're telling it to do, it still does what you tell it to do. It doesn't do anything to help you. Of course, that's actually good, to force you to pay attention to what you're doing. This is a pretty good match. What happens to this match if this is not a good SWR? Have we really balanced this all out? Or what have we really done? Let's make this be, say, a 2-to-1 SWR. Make it be 25 ohms. Let's put a 2-to-1 circle, 2-to-1 SWR circle here. And we can see that we started off at a 2-to-1 SWR, and we end up here pretty much at a 2-to-1 SWR. At some frequencies along the way, maybe we got up to 2.06. But this is not the same impedance out here as is here. These did not compensate and eliminate the effect of these pieces of transmission line. They just compensated the SWR. I hope that makes sense. So we started off here at 25. We end up here somewhere, at low frequencies we stay at 25, of course, but at 150 megahertz, we start off at 25. We end up here at 63 minus J, 37.4. If this is a 100 ohms, we see again a rotation. End up close to that 2-to-1 SWR. Here the SWR is a little bit lower. Fundamentally, it's still 2-to-1 pretty much everywhere. We pick a point like 40 minus J30 is a 2-to-1 SWR also. Again, we see it's still a 2-to-1 SWR, but what we don't see, it's still a rotation. So it does work for us. This compensation works nicely. It gives us pretty much the same SWR as what we had coming in. And it does give us a 1-to-1 SWR if the input happens to be 1-to-1 or 50 plus J0. To do this, though, it required me having a small VNA, which is one of the things that a small VNA and an NEC program really helps SimSmith. SimSmith needs those things to really be valuable, in my opinion. The ability to do this kind of stuff is based on the fact that I was able to guess at an impedance, but it really made it practical when I was able to measure the impedance of a circuit I had and then compensate for it. I did compensate that circuit years ago when I learned how to do this, and it kind of reminded me of a story a long time ago when I was a kid where I had this antenna switch that came from piece of military gear, and I took it apart, and it looked like there were some extra wires, and it had been built by some fool in some factory. And these extra wires were on the center conductor of the coax connectors that came into this device. And what they were pieces of wire that were wrapped around down near ground around a aluminum or steel pillar or something, and they were capacitors. And I never realized that, and I cut those off. Summarily, thinking that I was improving the circuit, which obviously was not correct. And humor is being able to make fun of yourself. Anyways, hope everyone's enjoyed this video, but SimSmith is really practical in being able to help do impedance matching and stuff like that on circuits that we run into all the time. Hope everyone enjoyed it.